In lab today, we learned how to analyze our data from last week's lab. Last week, we went out and dropped grids out in an area of grass to determine the dispersion pattern of ragweed. We are going to calculate the coefficient of dispersion, CD. We do so using the variance to mean ratio from our data. Now, when we do this, we're going to get a number that's going to be anywhere from 0 all the way up to possibly 3 or 4 or 5. And the question is, what happens if we repeat our sampling? So we did do that. Monday's lab collected in the same area as Tuesday's lab, who collected in the same area as Wednesday's lab, and who collected in the same area as Thursday's lab. And when we calculate our coefficient of dispersion, every lab is going to have a slightly different value. We also did it with grids versus transects. We sampled the same area. We're going to get a different coefficient of dispersion every time we sample it. So if we calculated a coefficient of dispersion equal to 0.9, based on what we've learned in lab, we would conclude that that is a uniform or regular dispersion pattern. But is it? How likely is it that we could get a value of 0.9 if our ragweed are actually random? Well, in order to answer that question, we're going to have to use some statistics. So what we're going to do is calculate our coefficient of dispersion, and then we're going to do a t-test. Now with our t-test, we are testing if our coefficient of dispersion is equal to 1. So that's our null hypothesis. Our alternate hypothesis is that the coefficient of dispersion is not equal to 1. We're going to test these hypotheses by calculating a t-observed value. This t-observed value is going to utilize this equation. Coefficient of dispersion minus 1 divided by square root of 2 over our sample size minus 1. When we calculate this t-observed, we are going to compare it to a critical value that we pull from a table. If our t-observed is less than that critical value, then our p-value will be greater than 0.05, and thus we conclude that the coefficient of dispersion is equal to 1. If our t-observed value is greater than or equal to that critical value, then our p-value will be less than or equal to 0.05, and we conclude that the coefficient of dispersion is not equal to 1. Well, what is all of this? Well, what we're doing is trying to come up with a probability of actually getting data as extreme or more extreme just by chance alone. So for example, if we calculated 0.9 as our coefficient of dispersion, we want to know how likely is it that we could actually get a value of 0.9 or something even smaller if the ragweed were randomly distributed out in our sample. And that's what this p-value is telling us. So by rule, if the probability of getting data as extreme or more extreme is 5% or more, then we say that it's entirely possible that chance gave us that value. That random chance produced that strange value that is not actually equal to 1. If our probability is less than 5%, then we say that the probability that the chance actually gave us this difference is so small that something other than chance gave us that value. And what is that something? Probably it's going to be the actual distribution of ragweed in that grass area. So what I'm going to do is step you through how to analyze one set of data so that you can then do the homework and also analyze your own data. If you missed lab this week, please contact your instructor and they should be able to supply you with the data that you collected last week. So here's a sample data set collected from grids. We recorded how many ragweed were in each of our grids, and then I assembled all of those data and made this frequency table. So we have number of ragweed range from 0 ragweed in a grid all the way up to 11 ragweed in a single square. Now we had 201 grids that had 0 ragweed, 46 grids that had 1 ragweed, 9 grids had 2 ragweed, 10 had 3 ragweed, 4 had 4, 1 grid had 5 ragweed, 2 grids had 6 ragweed. We had 0 grids that had 7, 8, and 10 ragweed. 1 grid had 9 ragweed, and that 1 grid had 11 ragweed. So in total, if I utilize the sum function and highlight this column, for this lab's data, we had 275 grids that were counted. Now your number will vary because we had different number of groups that performed this experiment in each of our labs. So in this group, if each group did 25 grids, how many groups did we have? Hopefully you say 11 groups. And if you did, then you're right. So we want to take this data and we want to calculate our mean, our average, which is our x bar, and we also want to calculate our variance, which is this s squared. We need both in order to calculate our coefficient of dispersion. So how are we going to do it? Well, I include our equations here. So our equations for a mean is the sum of our x's over our total sample size. So this is our sample size. I'm not sure what happened. Again, let's try this one more time and align it to the right. There. So this is our sample size, 275 grids. What we want is the sum of all of our x's. Now I worked out how to do this in the lab by using x and f. So the number of ragweed represent all of our x's, and f is our frequencies. It's how many of our grids actually had zeros in them. So our data set would be 201 grids had zeros in them. Now if we want to try to calculate this average, what we're going to do is do x times f. So I'm going to use this column, B3, times C3 to get x times f. And then I'm going to left click and hold and fill to get an x times f column. So if we are looking for the sum of x, we know that we have 201 zeros, and that means the sum of all of those zeros is 0. We have 46 ones. The sum of all of those ones is 46. We have 9 twos. The sum of all of those twos is 18, and so forth and so forth. So that we can take the sum of this column now, so D3 to D14, and that gives us 147. So this is the sum of our x bar, sum of the x bars. So what's our average? Our average is going to be this value divided by this value. That is the sum of our x's divided by n, and we get 0.53455. So this average tells us that if we drop a square in that grass area, we expect to see 0.5 ragweed every time we drop it. So that's our average. Now we have to figure out our variance. Our variance is s squared. This variance is using this equation. And in the lab, I actually utilized a slightly different format. So what I did was say we're going to take x squared and then we're going to multiply it by our frequency. Now some of you that have had a math stats course would recognize this equation as our variance. Well, if you expand this, this is how it would simplify it. So we're going to take the sum of our x squareds. Well, which ones are our x's? It's this column. That is our x's. So we're going to square each value, and then we're going to multiply it by the frequencies. So what I'm going to do is use my parentheses, and I'll say I want B3, the caret symbol, 2, and then I'm going to multiply it by this f column. Now, note, I did the f column. I did not do the x times f column. Then I'm going to fill this, and I get the x squared times f. But I want the sum of it, so I'm going to take the sum of this column. and I get 535. So now that I have that, and I have my mean, and I have my sample size, I can compute the variance. So I will use parentheses, and I will say we have that value, that's the sum of the x squared, minus our sample size, times the mean, or the average, squared. That's our numerator. And then I'm going to divide by this number minus 1. And I'm using parentheses to set off my numerator and my denominator. And when I hit enter, I get the variance. So just looking at variances and the averages, what dispersion pattern do you think we have? Well, if we have a random dispersion pattern, then these two values should be equal. They're not. Our variance is greater than the average, which means when we calculate our coefficient of dispersion, we should get a value that's greater than 1. So this is our variance divided by our mean, and we get a coefficient of dispersion of 3.11. Now we're not quite done yet. It suggests that our data, that our ragweed are clumped or aggregated, but we don't know that. We have to test first if this value is actually equal to 1. Or in other words, how likely is it that we could actually get a value that's equal to 3.11 or more extreme just by chance alone? So we're going to have to do a t-test. Our t-test first requires us to calculate a t-observed value. Okay, so our t-observed value is going to be a long equation. But we have everything that we need in our worksheet. So this is our equation. This is the absolute value symbol. So what we're going to do is I'm going to set up my numerator in parentheses, and then I'm going to do absolute value of my coefficient of dispersion minus 1. And that is my numerator. And then my denominator is going to be the square root, SQRT, of 2 divided by, and use one more parentheses, our sample size minus 1. And I close up our parentheses. So we're going to use this t-observed value to decide whether or not we accept our null hypothesis that the coefficient of dispersion is equal to 1, reject it, and conclude that the coefficient of dispersion is not equal to 1. So what else do we need? Well, we need our t-critical value. Our t-critical value is going to be pulled from a table. That table needs a degree of freedom. The degrees of freedom for a t-test is our sample size minus 1. So it'll be this n minus 1. How do I know that? It's in the lab manual. It's in our handout. It says that for the t-test, it will be our sample size minus 1, but it is this value, this n minus 1. That is our degrees of freedom. So how do we get it? How do we get our critical value? I have a handout posted on Blackboard that I had asked all of the students to print out and bring to the lab. And it's this t-table. So what this t-table is doing is giving us a critical value. And our critical values differ based on our degrees of freedom. So what we're going to have to do is go down to the appropriate degrees of freedom and then read across the rows to figure out what our critical value is. Now, which row do we use? For this class, we will always use this column here, this 0.05. And you might ask, well, what is this? Well, this row, this top row refers to alpha 2. This is a two-tailed test if you've had statistics. And this row under here is a one-tailed test. For this class, we're always going to use this 0.05 column for a two-tailed because we're going to test if our value is equal to some number or is it not equal to some number. So we will always use this column. So what we want to do is read down this column until we get to our appropriate degrees of freedom. So I continue on to the next page, keep reading down, and I get to this area. So we have degrees of freedom goes 200 and then it jumps to 400. what do we do? Well, by convention, if we have degrees of freedom that falls between any of these numbers, we always take the smaller number. We want to be conservative on our tests, and we want to make it harder for us to actually reject this null hypothesis. For us, it doesn't really matter. Our degrees of freedom are so large that there really is no difference between these two numbers. So our critical value here is 1.97. So 1.97. And now once we have that, our t observed and our t critical, we make this comparison. Is t observed less than or greater than our t critical? It's greater. It's much, much greater. So our t observed is actually greater than the t critical, which means our p-value is going to be really, really small. It's actually very unlikely that we would ever obtain a coefficient of dispersion that's 3 or higher just by chance alone if the ragweed were actually randomly distributed. So if it's not likely that we could get this value as large, then we conclude that our coefficient of dispersion must not be equal to 1. So that leaves us with the option of either being uniform random or uniform regular or clumped and aggregated. Well, our value is 3, it's greater than 1. We therefore conclude that ragweed is clumped or aggregated in that area. So this was for the grid, and you can use this video, pause it, rewind it, and rewatch it to see all of the functions. Obviously, you might not have 11, maybe you have 12 or 13, maybe you only have 6. Nothing changes. It just make sure you highlight the appropriate roads and you do the calculations to obtain your average, your variance, and then your coefficient of dispersion. And once done, then do your t observed, pull your t critical from a table, and make our comparison. If you have questions, please ask.